These are your 2-8 notes where we're going to be graphing inequalities. And so in this section, we're going to review. A lot of times in the book, after we go through everything with the regular functions and equations, then we look at the function in terms of an inequality. So when you graph an inequality, you're going to graph the related equation as the boundary. So what we're going to have is we're going to have a line, and then what that does is it creates two boundaries on the coordinate plane. So you'll graph the inequality as the equation, and then that creates a region above the boundary line or below the boundary line. If the inequality is less than or greater than, then the boundary line will be broken. And so what you have to do is physically break it. You can do this railroad method, or if you wanted to, you could make it dotted, as long as I can see that it's broken. And a dotted line or a broken line on the coordinate plane is similar to an open circle on the number line. We do not include those numbers, so those ordered pairs will not work. If, though, the inequality is less than or equal to or greater than or equal to, then the boundary line is solid, and that's our symbol that says the ordered pairs that fall on that line are also included. So just like a solid or filled in circle on the number line. After you create the boundary line, you have two regions. You have the region of values above the boundary line, and then you have the region of values below that boundary line. For an inequality, you'll either be shaded above, which represents all the solutions that work above the line, or if the solutions are below the line, you'll shade below the line, just like we did on a number line. We shaded the direction of the arrow. So to determine shading, the shading is the ordered pairs that work. And so you're going to pick a point, not on the boundary line, to determine shading. And we always shade true. So if you look at my graphic up in the corner, I can pick an ordered pair in the green region. If I pick an ordered pair in the green region, any number, for instance, 0, 0 is a great number to pick because it's easy to plug into an inequality. You plug it into the inequality. If it gives a true result, we would shade in the green area. If it doesn't give a true result, if it's a false statement, we would shade opposite, so we would shade in the red. Somebody next to you, or your neighbor, might pick a point in the red region to pick for shading. And so if they pick an ordered pair somewhere in the red region and it works, they'll shade red. If it doesn't work, they'll shade green. So we always shade true, but you don't have to pick more than one point. So let's go ahead and try this. So we're going to graph the inequalities. Notice it has an inequality greater than symbol rather than an equation, equal sign. But to get the boundary line is the actual equation that matches that inequality. So I'm just going to temporarily change it to an equation just so I can get my boundary line. I notice that this is in slope-intercept form, and my slope is equal to 1, and my y-intercept is equal to -1. So I'm going to go over to my grid, and where the slope, I'm going to start at -1 on my y-intercept, and I'm going to count up 1 over 1 for my slope, up 1 over 1, up 1 over 1. So I have enough points to connect and extend. There's my boundary. And so my boundary creates two different regions on the graph. I have the numbers above that line, and I have the numbers below that line. I look at my inequality, and I realize that the inequality is greater than, and so the ordered pairs that I just used would equal, not be greater than. So this is where I have to break my boundary. So I'm going to put a little note to myself as to why I'm breaking it so that you can reference this. And also in January, when you're taking the exams, it's nice to have a nice note. So if I were to plug any of these ordered pairs into that inequality, it would give me a solution like 3 less than 3 or 5 less than 5. And that's not a true statement, so those numbers don't work. The only way they would work is if we said equal to. So now that I have my boundary broken, I know I have two different boundaries. I got to pick a point to check. So if you look at my graph, we always pick a point not on the boundary. An easy one is 0, 0. You cannot use 0, 0 if the line goes through 0, 0. And you want to make sure that you know that 0, 0 is clearly in that region. So I know, according to my graph, that 0, 0 truly does belong above this boundary line. It wasn't that I was sloppy. So I'm going to pick 0, 0. Notice I marked it, and 0, 0 represents every point above that boundary line. So I'm going to make a little check mark, and that just tells me that I'm checking, and then I'm going to write down the ordered pair that I'm checking with. I'm checking with 0, 0. I'm going to use the original inequality. So I got to go back to the original inequality, y greater than x minus 1. I'm going to plug 0 in for y, and I'm going to plug 0 in for x, and I'm going to solve. I put a little question mark above my inequality because that tells me I'm asking. I'm not saying it is, I'm asking, is 0 greater than 0 minus 1? And if I simplify that, is 0 greater than negative 1? The answer is yes, that's true. That's a true statement. Okay, 0 is greater than negative 1, that is true. And so where 0, 0 lies, that was the ordered pair that represents all ordered pairs above. And so since 0, 0 was true, all of the ordered pairs that are above that line are true. And so what we can do to show that, to show the answers, we can't actually write down the answers. All we can do is draw a picture of our answers. We will shade above the boundary line. And the shading represents every ordered pair above this boundary line will work for that inequality. I can pick any ordered pair in that shaded blue region, plug it into the inequality, and it will work because 0, 0 worked. If I plug 0, 0 in and it gave me a false result, then I'd have to shade the opposite side. I do want to show you really quick, if I were to use the ordered pair right here, that's the ordered pair 3, 0. If I decided to use 3, 0 to do my check, which you will not have to do 2 different points, I just want to show you, when I use the inequality, I plug 0 in for y and 3 in for x. Is 0 greater than 2? And that's a false statement. And so that's why we wouldn't shade on that side. If I use 3, 0 as my point to check and I got false, that tells me that every point lying below the line would be false, and so then we'd have to shade opposite. You could only be true on one side of the boundary. Let's try another one. 3y minus 2x less than or equal to 6. So when I write the equation, 3y minus 2x equals 6. And I notice that x and y are on the same side. When x and y, the variables, are on the same side of an equation or an inequality, sometimes x and y intercepts are the easiest way to graph. So I'm going to use x and y intercepts, and I like to call this my peekaboo. So I'm going to just draw this nice little green finger, okay? And if I plug 0 in for x, that goes away, and I have the equation 3y equals 6. So my y-intercept is when you plug 0 in for x, and my y-intercept is 2, or we can write that as 0, 2. So I'm going to go over to my graph, and I'm going to plug in 0, 2, plot 0, 2. If I plug 0 in for y, my 3y will disappear, and I have to solve the little equation, negative 2x is equal to 6. And that equation, when you solve it, x is equal to negative 3. And so my x-intercept is negative 3, 0. Negative 3, 0 on the x-intercept. So it's a nice, easy way to get my graph. I got 2 lines. I connect and extend, and that creates my boundary. I notice that up above, this line right here represents equals to. So that means my boundary is going to be solid. So I'm not going to break that line. And now I've created 2 boundaries. I have a boundary above that green line and below that green line. So I'm going to pick up 0, 0 again. 0, 0 is clearly below that boundary. So 0, 0 represents every ordered pair below that boundary. So when I check with 0, 0, I'm really checking every point below that boundary. So I use the original inequality, 3y minus 2x less than or equal to 6. I plug 0 in for the y value, and I plug 0 in for the x value. What's nice about using zeros, though, everything just disappears. So I'm asking, is 0 less than or equal to 6? And the answer is true again. So because that's true, I'm going to shade below this time. You shade true. So this time, my answer was true below it. Last time, it was true above it. You always shade true. That means those are the solutions. And when I shade, I'm shading because I can't name all these ordered pairs. There's so many ordered pairs, nice numbers, rational numbers, irrational numbers, and we don't skip any. So it's my way mathematically to say, if you find an ordered pair in that green region, it's a solution. Now, if you didn't like the method of playing peekaboo to find your graph, you could easily take that equation, that 3y minus 2x equals 6, and put it in slope-intercept form. So some of you guys might want to add 2x to both sides. 3y equals 2x plus 6. You might want to divide everything by 3.
Can I please have the following students to the office at lunch? Jake Hassan, Elizabeth.
If we solve, we divide both sides by 3. You get 2/3 x plus 2. So if you wanted to, you could put the equation in slope-intercept form. Your slope would be 2/3.
Also, any junior.
Sorry about all the interruptions. So your slope would be 2/3, and your y-intercept would be 2. We'd still get the same line. I'd start at 2, and then I would just count up to over 3 for my slope, down to over 3 for my slope. So you do not have to use x and y intercepts to graph. I give you a little bit of freedom there. You can make a table of values if you so desire. Next problem, negative 3x less than 12. Notice we're missing one of the variables, which means we're only going to move in one direction. So negative 3x equals 12 is the related equation. If I divide both sides by negative 3, I get the equation x equals negative 4, which I'm hoping by now you recognize is a vertical line. This symbol right here says less than, and so it's going to be broken. I'm going to make a note over here, so later on I can realize why it's broken. This symbol right here is why it's broken. So I'm going to break the line, and that means the ordered pairs on that line will not work. Now, instead of saying above or below the boundary line, now we have to the left and to the right. So when I pick my point, not on the line, I can use 0, 0 again. When I check using 0, 0, I plug it into the original inequality. And so I get negative 3 times 0 is less than 12, or is 0 less than 12? Is that a true statement? 0 is less than 12, that's true. And so we shade to the right. Again, if you were to plug any numbers into from the left side, you would have gotten a false result. So I did show you 3 examples where you got true each time. You just flip your shading if you get a false reading. Okay? So the lesson summary. Oops. I want you to describe when do you use a solid boundary line or a broken boundary line, and then I would like you to graph the inequality y less than x plus 3. Good luck.